A shape-shifting body. Atomic computing, powering a brain that might outsmart our own. The rise of the machines may be closer than you think. I'm Dr. Michio Kaku. I'm a theoretical physicist and a science fiction fan. Join me as I show you how to make sci-fi science.
You have been brought here for a purpose, the most important task of your lives.
Intelligent robots rule science fiction. They've been mercenaries, fugitives, translators, best friends, and worst enemies. When I was a kid, I thought that by the 21st century, real intelligent robots would be everywhere. But it turns out that making a machine that's as smart as us is a tall order. And what's more, we've all seen what happens when robots go bad.
Do not make it destroy you.
Robots have been going out of control in the movies for decades. I want to design a robot that's just as smart as a human and can help us with our everyday tasks. A robot that's a companion and colleague, but not an enemy. But first, I need to check what a true sci-fi robot ought to be able to do. Who better to ask than the sci-fi fans themselves?
In order to navigate their environment, they have to be able to recognize the environment.
Yeah, it's definitely going to be able to recognize humans and has to be good at it because, it might mistake it for, I don't know, cattle, kill it, process it into meat, then you're eating a human cheeseburger.
A robot needs to have common sense. It needs to be able to learn from its environment.
My dream robot would have the brains of C-3PO, and like a transformer, it'd be ready for anything. To succeed, it needs 4 things. It must be able to see and recognize the world around it. It must be able to make its own decisions and learn from experience. It needs super fast computer processors to equal the speed of the human brain. Its body must be tough and versatile so it can deal with any environment. My first challenge is RoboVision. We take it for granted, but sight is the most complex of our senses. About 1/3 of our brain is devoted to seeing. It's so complex, no scientist has come close to building a machine that can replicate it. But at Stanford University, robot designers are on the verge of a breakthrough. This is the world through the eyes of STARE, the Stanford Artificial Intelligence Robot. STARE sees through a high-resolution camera and scanning laser. To recognize objects, it compares what it's looking at with images in a database. It's like solving a jigsaw puzzle. First, the robot takes an image and breaks it up into millions of tiny pixels. Then it identifies patterns in this image and compares it to a database of thousands of images inside its memory. By constantly referring back and forth between the patterns and the images in its database, it makes a match and recognizes the object. That's the theory, but I want to see it work in practice. So I've set STARE the task of picking out a coffee mug from a bunch of similar objects. For us, this is second nature, but for a machine, it's very hard because it sees a jumble of contoured lines and shapes, many of which to it look exactly the same. So STARE's creators designed a simple solution.
What the robot does, if it doesn't know what this object is, then it will go and move the object around to a location.
It'll turn it around.
Turn it around, exactly, and it will see it from a new point of view, and then it will be able to grab it or say what the object is.
STARE needs a perfect match before it can identify something. It needs to see an object from all angles.
Now it was able to see a better view of the mug with the handle, so now it knows it is a coffee mug. Now it's going to give the coffee mug to you.
Oh. Well, thank you, STARE. Thank you very much.
STARE is cutting edge, but clearly we have a long ways to go. It took over a minute to complete a task that takes me 1/10 of a second. But what I've seen has potential. It just needs an upgrade. First, I give my robot a camera and laser eyes to look at the world. Next, I'd upload a database containing not thousands, but billions of images, a catalog of nearly every object my robot is likely to encounter. It may take decades of work, but in principle, my robot can now recognize as many things as a human. A good start, but as sci-fi fans know, recognizing objects is not enough.
A robot has to perceive objects in the environment, has to understand what it's seeing.
If you ask them to bring the book from the bedstand, you don't want them to bring the bedstand. You want them to bring the book.
It's the difference between just reading video and understanding what it's seeing.
Recognition is the easy part, but learning the rules of an unpredictable world, that's hard. I'm designing a robot straight out of sci-fi. So far, it can see and recognize things, but that's not enough. My robot needs to be able to make decisions, and for that, it needs what AI researchers call common sense. Common sense is crucial. Without it, we'd forever be hurting ourselves and making simple mistakes. Virtually every human action is based on common sense decisions. Take the journey I make every day from my office to the subway station. This trip is second nature to me, but even so, the unexpected happens every step of the way. I have to navigate a safe course around pedestrians, all following their own unpredictable paths along the sidewalk. And when they stop for no reason, I have to react quickly to work out how to get around them. When I come to a crosswalk, I have to judge the best time to dodge traffic. I even have to watch out for tiny changes in the surface I'm walking on. It might look the same day after day, but my environment is in fact constantly changing. My brain is able to cope with all these uncertainties because it makes literally millions of subconscious decisions about every aspect of my journey. This is common sense at the most basic level. To operate in the real world, my robot needs to emulate our brain's ability to learn and process common sense. Robot engineers have been trying to do this for decades. Their initial attempts fed computers with lists of rules. But they found that human levels of common sense would take lifetimes to input as a set of instructions. And no matter how fast their computers process this code, not one developed true common sense. Scientists now realize that we have a bottleneck with regards to this design. The Pentium chip basically is an adding machine. All it does is it adds 1 + 1 is equal to 2, but it does this billions of times faster than the human brain, so we have the illusion that it's thinking. This approach was flawed. The brain is not a digital computer. It's a neural network, a web of billions of neurons designed to learn. So we now believe that the brain actually consists of a series of neurons connected in very complex ways, and that after it masters a new task, it reinforces some of these links. So the brain literally rewires itself after performing every given task. This is a neural network. It's a learning machine. Armed with this realization, robot engineers are now building robot brains differently. Enter a robot with an artificial neural network. Called Logger, it autonomously navigates its environment. Every time it runs, Logger analyzes feedback from the surroundings and rewires its neural network. The more it experiences, the more it learns. Professor Yann LeCun is the lead scientist on the Logger project. He's agreed to show me the secret of how his creation works.
Okay, so what you're seeing on the screen here is the world view of the robot. The green areas are the area of the image that the robot labeled as traversable, whereas the red areas and the purple areas are the ones that are identified as being obstacles.
So the robot wants to avoid the red areas by going through the green areas.
Exactly. It will try to find the shortest course that takes it to its goal. And while it's doing this, it's learning to discriminate obstacles from traversable areas.
Professor LeCun wants to prove to me Logger's abilities, so he's set it the challenge of navigating a course it's never seen before. He's already put Logger through hundreds of hours of training in tricky obstacle courses. So if Logger is really a learning machine, it should tap its neural network for previous experiences and use them to tackle the maze. Logger gets off to a flying start.
All right, so now it's getting to the kink in the maze, and it's seeing the obstacle in front of it, and it's taking a turn, and pretty soon it's going to see the other part of the maze. It's sort of turning all the way to the right and getting out of the maze.
Logger raced through the course in record time. Perhaps the task I set it was too easy, but it's the principle that matters. Neural networks are the way to go. My robot's neural network would combine advanced hardware and software to simulate not just a few neurons, but several billion. More neurons equal more potential to learn new experiences. So over time, my robot will learn enough common sense to operate by itself. I'm making good progress, but I'm still not even close to what sci-fi fans expect.
An intelligent robot should be able to think faster than a human at the very least.
I say he's got to be very smart, obviously. Maybe not as smart as humans, because there's that whole entire thing that they'll rebel and kill humans. So I'd say a little bit dumber than humans.
My robot needs to be super smart, but not too smart. Robots in the movies are often just as smart as us.
Well, that's fantastic.
Scientists estimate our brains perform up to 20 million billion calculations a second. So my robot needs extreme computer processors. But they won't be built from silicon microchips. Instead, they may compute on individual atoms, creating a computer thousands to millions of times more powerful than anything we have today. Welcome to the world of quantum computers. At MIT, researchers are building prototype quantum computers that transform atoms into calculators. Inside this metal drum sits a test tube of atoms cooled by liquid helium. Instructions are relayed from a computer via a console that zaps the atoms with microwaves to make them compute. One of the scientists on the project is Professor Seth Lloyd. I want to know whether his research could create a processor fast enough for my robot.
So current quantum computers are rather big, as you can see, because it takes a room full of apparatus to talk to an individual atom and to have the atom talk back and be understood.
Conventional computers are very simple. They calculate using electrical pulses with only two values, 0 or 1. Quantum computers are different. They compute by spinning atoms in opposite directions. But because they're atoms, quantum mechanics opens up a load of weird possibilities. In our world, objects exist in definite states. Objects are either up or down. They're either on or off. And for computers, numbers are either 0 or 1. But in the bizarre quantum world, objects exist simultaneously as a mixture of states. If I were a quantum state, it means that I could exist at the same time in multiple places. Instead of being here or there, I could be here and there and everywhere in between. Because a single atom has an almost infinite number of states, it can participate in an almost infinite number of simultaneous calculations.
An ordinary computer is something like a single line, a Gregorian chant, you know, do, na, noise, do, mi, ne. Whereas a quantum computer is performing many lines at once. It's like a symphonic effect in which you have many, many different lines that come together to make the computation. And it's this ability to do quantum multitasking that separates quantum computers from classical computers, and it gives them their power.
In fact, scientists estimate that a quantum computer with the same number of atoms as a sugar cube would outperform all the computers on Earth combined. The raw computational power of a quantum computer is truly mind-boggling. Theoretically speaking, there's no reason why a quantum computer can't keep up with and even exceed the power of the human mind. I could be waiting many decades for a quantum computer, but when it's a reality, it'll fit right into my design. If I plug the neural network and image database into a quantum computer, both get a massive speed boost, instantly processing data as fast as a human brain. But a quantum-powered robot raises serious concerns. What if the CPU is too powerful?
I will be able to conquer the galaxy.
Science fiction is full of robots that run amok. What if my super robot turns on me, like in The Terminator or The Matrix? But there's no guarantee that a quantum computer will send my robot mad. After all, for every HAL, there's a C-3PO or Commander Data.
Good work, John.
But to make sure I don't create a merciless killer robot, I should watch out for any signs of murderous thoughts. Get more at sciencechannel.com/sci-fi science. I'm designing a futuristic robot straight out of science fiction. There's just one final component I need to add: a body. Decades of sci-fi movies have made us think that a robot should be humanoid. But robot engineers at the University of Southern California have taken a very different approach. This is Superbot. It's not just one robot. It's actually a collection of separate modular units that can recombine and reform to create an entirely new machine. In one configuration, it could crawl like a snake. In another, it can roll like a tire. And in another, it can actually climb a rope like a monkey. It's like a real-life transformer. If my robot was modular, it could adapt to any situation by simply changing its shape. Superbot's secret is its hive brain. Each module is independent, but they can cooperate as one big brain, like a swarm of bees. The advantage is, if one module breaks down, it's easily replaced, but it could also be a big problem. I'm already worried about my design's quantum computer, untested technology that could turn my robot bad. Put quantum computers in each module, and I run the risk of creating a hyper-intelligent superorganism which might not be friendly. I better make sure this never happens. It's vital that I install a circuit breaker chip, so if my robot does go berserk, I can pull the plug and avert disaster. My robot's tame and its design is complete. It's not exactly Commander Data, but it has the potential to be a truly intelligent robot. It's time to show it to the sci-fi fans. Ladies and gentlemen, tonight I'm going to present to you the design for an intelligent robot. The world's first intelligent robot steps off the production line and into a test facility. The robot's neural network sparks into life, processing the data from its environment, continually rewiring itself as it learns new information. This gets smarter and smarter and smarter because it learns after every task. The robot encounters an obstacle. It cross-references what it's seeing with this image database. Within milliseconds, the robot has a match and recognizes a wall. The robot needs to get past. The neural network analyzes the situation. It runs at lightning speed because it's powered by a super-fast quantum computer. The robot makes an instant decision: change shape. The body is deceptive because it is modular, because it can literally take itself apart, reform in any shape whatsoever. The robot rearranges the modules of its body into a snake and slithers through the gap. On the other side, it finds a slope. The neural network fires up and makes the decision to transform again to tackle the change in terrain. So there you have it, the intelligent robot, a robot that incorporates all the new thinking about artificial intelligence. But what do the fans make of it?
I really liked the part of the robot where it turned itself into a snake by unplugging little bits and plugging them back in its butt and getting all lean. And
the coolest part of the design was the way that the robot can sort of rearrange itself.
I think what excited me the most was the possibilities contained with that neural network approach, or the CPU, the brain, if you will.
I definitely did think that it was a very interesting design, very cool.
My favorite part was actually the brain. I liked the idea of it was a very, well thought out, almost natural brain.